Welcome to Chapter 3, Cluster 1, Lecture 13. So, we are taking a look at functions. Okay, so function sense. So the definition, a function is an input-output relationship in which each input value, and that should be a has only one matching output value. Okay, so note. The input variable is called the independent variable, and the output is called the dependent variable. That is because you need to first input the independent variable, and then you find out what the dependent variable is, or the output. So, first you put in the input, and then the output is whatever happens, which is why the output depends on the input. Alright, so function forms. Functions can appear in three different forms. So the first form that you would find are tables, or also just rosters or ordered pairs. Okay, so for example, for a table, you might have something like x, y, a 2 value for the x and a 3 value for the y, or maybe a -1 value for the x and a 0 value for the y. That would be a table. Or, for example, a roster might be, in your little braces here, we just list off numbers. That would be a roster. Or ordered pairs would be, maybe in this roster form, 1, 2, 2, 3, and so on. So those would be tables. Those are the ways that sometimes you just list out numbers. Another form is for graphs. So if you have your coordinate plane here, your x and your y values, you might have the graph of maybe a line. And that would be another way that a function can be shown. And one of the ways we use most often is the equation form. For example, y equals 3x plus 1 would be a function. Now, so the special thing to note here for when we're looking at functions, okay, this is very special, so please pay attention. Sometimes, instead of making someone guess if your equation is a function, other mathematicians will be nice and say, you know what, I'm going to let you know this is a function. And how will I do that? Well, I'm going to replace y with f of x. So when you see f of x equals 3x plus 1, because I see this notation called f of x, I'm allowed to assume this equation is a function. If we were just given this top one here, I couldn't assume it's a function. I'd have to spend time testing this to see if it's a function. So to be nice and to not have somebody waste their time testing things, or just spending that extra time, you would write f of x to indicate that this is indeed a function. So remember, f of x is a nickname for y. Y is the same thing as f of x. They're nicknames. Okay? That is a very casual way of putting it. Okay? So, note, for functions we often replace the variable y with, and as I said before, f of x. Very important to remember. And f of x is generic. Sometimes you might see g of x or h of x. But whenever you see that notation of x, you know that it's saying your equation is a function. Alright, so let's move on to identifying functions. So we're going to spend some time. Let's see. For example 1, identify whether the following are functions, y or y not. So the first thing we want to do, which has to do with the definition, is remember, the definition states it's where each input has only one matching output. So that's what we're going to look for. We're looking for each input has one output. And oftentimes, generically, the input would be our x value, and the output would be our y value. So let's take a look at these right here for A. Well, an easy way to check this is I like to set up a table and list out my x and y values and see if I have any duplicates for my y. So for x value, I have 2, 3, another 3, okay, well I just already wrote 3, and negative 4. Now let's list out our y values. I have negative 3 for the 2, 4 for the 3, and then a 1 for 3 as well. Okay, well we have 2 y values for that x value, and then 5 for the negative 4. So real quick, what's the definition for a function? Remember, the definition for a function states each x value should only have one y value. Notice this x value has 2 y values. This is not a function, okay, because the definition says this shouldn't happen. So no, it's not a function. Ooh, that's a really ugly looking. Let me spend a little more time rewriting that nicely. Okay. No, it's not a function. And the answer to y would be, let's do a capital there, each input, wow, that's a messy each input, I did it again, wow, that's pretty bad. Each input real quick, back up here. Each input does not have only one value. So we can say an x value has more than one y. Okay, so that is the violation there of the definition of functions. Okay, so take a second and look at B and check, is that a function? Pause the video and check in with me in a second. Alright, well as usual, I like to just go ahead and maybe draw a table. Well, let's see. For the x values, you have negative 1, 3, negative 1 again, 7, and 5. And then for the y values, we have 2 for the negative 1, 0 for the 3, 6 for the negative 1, 7 for the 3, and 4 for the 5. Oh, notice it happened again. We have one x value, but it has 2 y values here. But notice, remember, each of these values are okay. They each have only one y for each x. The problem is, if one person, or one number in the group violates this rule, it is no longer a function. Okay? So no, this is not a function. And then another way you could state it is each input does not have only one output. Okay? So as long as you're stating that your input value or your x value does not have only one y value. It's a good way of explaining it. Alright. So we're going to go ahead and evaluate functions. So when it says evaluating functions, often what you're doing is you're just plugging in a value and simplifying until you find your number answer. And sometimes you don't even find a number answer, but you're just inputting values and seeing what you get. So for this one, we're given the equation f of x equals negative 2x plus 5. So I have a real quick question for you. Is this equation a function? If you say yes, why do you think it's a function? Okay, so the answer is yes, this is a function. Why? Because it has f of x. When I write f of x, I'm telling other mathematicians, which are you guys, I'm telling you that this is a function. So you don't have to spend time guessing and checking. Alright, so we already know it's a function. So what we're asked to do, or we're told, is we have this function, and we want to find f of 1. Well, let's unpack this first. F of 1. Remember, normally we have f of x. So what happened here? Well, we have just taken out x and we have replaced it with 1. And that's the plan. The plan is take out x values and replace it with 1. Alright, so go ahead with that. So first, we're going to identify where the x values are, because we're going to replace them with 1. So we're replacing x with 1. So where is x in this equation? Well, it's just right there, being multiplied to the negative 2. So we're going to go ahead and replace the x with 1. Replace that with 1. And let's rewrite this equation. So we want f of 1 equals to negative 2 times, and we're replacing that x with 1. Why are we doing that? Because I've indicated here I want to replace the x with 1. And then we're just rewriting down that plus 5. So let's go ahead and evaluate this. Negative 2 times 1 is going to be negative 2. Bring down the 5. And then we have 3. Negative 2 plus 5 is 3. We'll go ahead and writing this down here, the f of 1. So that means f of 1 is 3. All right, for b, what are we asked to do here? Well, we're given g of x. Okay, now remember, real quick, g of x, that's just a generic function form, so this function's name is g. The previous function's name was f. All right, the reason why they are given different names is because equations are different. So we wouldn't want to give everyone the same name. For example, if all of you in class had the same name, that would make grading very difficult. So to differentiate between different types of equations, mathematicians will give them different names. All right, so for this equation, it says replace the x value with negative 1. So let's go ahead and look in our equation. Here is the x. Well, x is right there. So let's go ahead and replace that with negative 1. So g of, and we're using negative 1, equals 3 times, and we're replacing the x value here, we're replacing that with negative 1 plus 4. So that's going to equal 3, negative 1 plus 4. 3, and that's going to be negative 1 plus 4 is 3, so that'll be 9. So just copying this down. Notice lining up the equal signs nicely. G of negative 1 equals 9. So we have evaluated this function with the x value of negative 1. Which means when our x value, so when x is negative 1, what is our y value? Well, remember, y is the g of x value. So that means that y is 9. So just a hint. When x is negative 1, we found out that y was 9. Alright, so take a moment, pause the video, and try C and D by yourself, and then check back in with me in a second. Alright, so for C, we're going to replace x with 2. So here's the two x values we're replacing with 2. And let's go ahead and work this out. So h of 2 equals 5. Now times, careful, that square is being applied to the whole base of 2. Minus 2 times, and once again we have, so this time x appeared twice, which is kind of fun. So that's going to be 5 times 2 squared, which is 4, minus 2 times 2. So 5 times 4 is going to be 20, and then minus 2 times 2 is 4. So 25 minus 4 is 16. So h of 2, and if you want, instead of having to rewrite that a bunch of times, you can just go ahead and say, I'll allow that. Some instructors would not allow that, so it depends on your instructor's preference. But if you go ahead and show that, that'll be fine. And lastly, let's go ahead and identify where the variable is. Oh, now this one's weird. We aren't told to change the x value. It's still x. What are we told to change? We're told k of x equals 6. So where is k of x in this equation? Well, k of x is right there. Ooh, this is sneaky. So this time we're not trying to find y. This time we're given the y value, 6. And then we're trying to solve for x. How sneaky. So we're solving for x. And we know how to do that. We've solved equations before. So let's go ahead and subtract 3 from both sides. So that'll be 3 equals 3x, and then we'll go ahead and divide both sides by 3. And we get 1 equals x. So when k of x equals 6, we know that x equals 1. Just a little hint there. Alright, example 3. We're told to graph. Oh, sorry. This is the graph form for functions. So A, plot the points -5, -2, 0, 0, and 2, 1. Well, since I don't have tick marks, I'm going to go ahead and create some of those myself. So let's go ahead and do the negative x values. 1, 2, 3, 4, 5. So this is just a very basic plotting. If you needed to make something very exact, you would be supplied with an actual graphing point. Or, an actual graph paper. So -5, 2, that's the x values. We're going to go back -5. 1, 2, 3, 4, 5. And then we're going up 2 values. Sorry, down 2 values. Excuse me, that's a negative. So down 2. 1, 2. And there we go. -5, -2. And then the point 0, 0. Well, I'm not moving anywhere from the x values, and I'm not moving anywhere for the y. So I'm just going to be plopped right here. 0, 0. And finally, 2, 1. So my x values are going to go over 2, 1, 2. And then up 1 for the y values. Boop. And please label your points. Whenever you plot points, please label them. As usual, always recommended to label as much work as possible. That way, when things are being graded, you can get more evidence put down on the paper to earn you more points. Alright, B. Draw a line. Ooh, that's supposed to be line, not ling. Draw a line through these points. Include arrowheads. Alright, so here we go. Best freehand. Ugh, that's not a good freehand. Let's try this. As good as it's gonna get. I have a question. Why should I include arrowheads? What's the importance with arrowheads? What is the difference between this and not having an arrowhead? Well, to a mathematician, if I read this, this looks like this line stops at this number, which would be, let's see, -5, -6, -7. So it looks like it stops at -7. So this to me looks like it doesn't include anything down in this direction because of that stop point. The arrowhead, on the other hand, tells me as a mathematician this does continue on forever in that direction. Okay, so to indicate continuing on foreverness, what you do is you put those arrowheads. So if you see arrowheads, you know your line continues on infinitely in that direction. Okay, so arrowheads are important. Please, if you're ever drawing a line, include arrowheads. If there are no arrowheads, that is considered incorrect for a line, so points may be deducted. Alright, so here's a question. Does this graph represent a function? Why or why not? Well, you might want to sit there and slowly plot out for each x value. There's only one value. That could take some time. So the nice thing about having a graph is we have this handy-dandy principle, or test, excuse me, which is right below our problem. The vertical line test. So what is a vertical line test? If you're given a graph, which we are, huzzah, if a vertical line is drawn anywhere on the graph and it intersects the graph in more than one place, then what? And it's not a function. Okay, so a vertical line, remember, what are vertical lines? Well, vertical lines are like this. So if I drop a vertical line somewhere on my graph, now real quick here, please note, the graph is this piece right here, okay? The graph is not those axes points, okay? So looking at my graph, if I drop a vertical line anywhere on this graph, if it hits it in more than one place, it's not a function. So let's just draw one line. Boop. How many places does it hit my graph? Well, just one place, so I'm good. Let's test a few more areas on my line. How about here? Well, it still just intersects in one place, so it's still a function. How about here? Still just one place, so it's still a function. So, does this graph represent a function? The answer would be yes. It passes the vertical line test. So for example 4, take some time and try practice drawing out the vertical line test. Pause the video and check back in with me in a second. Alright, so hopefully you've tried this by yourself. Which of the following graphs are functions? Why or why not? So the nice thing is, we have the vertical line test, and we have graphs. So let's go ahead and check this. For the first one, if I drop a line, that only hits in one place. Let's go ahead and drop a few more lines. Does it ever hit in more than one place? No. So this is a function. So, function passes the VLT. Okay, you can just shorthand vertical line test with VLT, vegan lettuce and tomato. All right. Let's do the next one. Dropping a vertical line. It's a little tricky, but yeah, this only passes in one place. So yeah, this is a function. So this here, if you're not certain about the shape of this, that's called a parabola. And it is always continually growing outwards. See the arrowhead indication there? That means it is continually moving outwards for infinity. Now let's look at the next one. Well, I drop a line here. That's fine. Here, fine, fine. Yeah, it checks out at every point. So this is going to be a function. It's a function. Passes the VLT. And let's look at the last one. Let's go ahead and drop a vertical line right here. And look, it only hits at one point. Are we good? No. Even though it passes at that one particular point there, if I drop another vertical line here, look what happens. It hits once, twice. Look at that. And right there again, it hits once, twice. Look at how many times this thing is violating the vertical line test. So it's failing the vertical line test, which means this is not a function. So not a function. Why? Does not pass the VLT. Okay, so as usual, if you ever are trying to figure out if something is a function or not and you're given a graph, use the vertical line test. It is a beautiful and simple test. Alright, let's look at the last page. So here's an application with functions. Liz enrolled in an 8-week health program to help her develop a healthy lifestyle through diet and exercise. The data given below in the table represents her weight W pounds in time T weeks. Okay, so we know that the weight is W pounds and time is T weeks. And we're given this chart. So let's try to take a moment and read this chart. What does 0 mean? Well, 0, this is the time. So in 0 weeks, she weighed 140 pounds. Well, explaining that, or describing that means, in the beginning, she weighed 140 pounds when she started the program. So what does it mean for the 3 and the 131? What does that mean? Interpret that. Well, that means that in 3 weeks, she weighed 131 pounds. Which then means down here, at week 7, she weighed 130 pounds. So if I was reading this chart, does it look like she lost weight over the 8 weeks? Yeah, because at week 0, she weighed 140 pounds, and at week 8, she weighed 126 pounds. So she actually did lose weight. So for part A, is this an input-output relationship a function? Why? Well, remember, to check for functions, we have two options. We can check the input and output, or each x should be only one y, or we can use the VLT. Well, we don't have a graph, so we can't use the VLT, which means we need to check the input and outputs. So these are our x values, generic x values, and these are my generic y values. Well, for each x value, there is only one y value, so we're good. This is indeed a function. So is it a function? Yes, it is a function. Because for each x, or for each input, there's one output. Okay, so for B, identify the input and output variables and write each input and output entry as ordered pairs. Alright, so the input variable is our time, because to figure out how much she weighed at a certain point, we're going to take a look at the time. Alright, so the input variable is time, and the output is the weight. So the weight is dependent on the amount of time that has passed. Alright, so we're going to write each input and output as ordered pairs. Ooh, I kind of used up a lot of space writing that out. Ooh, goodness. Alright. So plotting this out, first we need to write out our data points. So my data points, let me change the color here. We have 0, 140. And I'll use the roster method here. So that was 0, 140 I got there. And then we have 1, 136. So pause the video and write down the other ordered pairs. 2, 133 from there. 3, 131. 4, 130. 5, I ran out of room there. 127. 6, 127. Oh, she's going down in weight. 7, 130. Oh, she went up a few pounds. 8, 126. And let's plot the data points. So I'm going to make a makeshift graph here. Let's see. So we have our y values, which are going to be the weight. And then our x values, which is going to be the time. Oops, running out of space here. Time. So time, the x values just go from 0 to 8, which is pretty simple. So the 0 value to 8. So we'll do 1, 2, 3, 4, 5, 6, 7, 8. To fix this and put more space here. And then my weight. The largest number we see is 126. And the smallest number we see, oh sorry, that's not the largest. Largest number is 140. Smallest number is 126. So the numbers are all roughly between 100 and 200. So let's go ahead and do this by we can go ahead and do 100. Let's do 50s. So that's 50. There's 100, and then 150, and 200. So then in between 100 and 150 we get 125. And in between 100 and 50 we get 75. Alright, so let's go ahead and plot these points. 0, 140 is going to be 0. 140 is about there. 0, 140. I'm going to draw an arrowhead. 0, 140. Let me go ahead and make this a little bigger. So the next we have 136. So 1 and 136, it's going to be about here. Then we have 2 and 133. 2, 133. Not the best graph, but this'll do. It's a sketch. Then we have 3 and 131. So a little lower. Then 4 and 130. Five is 127. Six is also 127, so plateaued there. 7 was, back up to 130. And 8 was 126. So a very rough sketch of a graph. Alright, so before we continue with this problem, we're going to go into a few definitions. So domain and range. The domain refers to the set of possible input values. Remember, input values are generically my y's. So the domain and range are talking about, your x values, not your y's. The domain refers to your y values normally. So how I like to think about it is when somebody is talking, like an animal is talking about the domain or something, the domain of the animal. You're talking about the ground that the animal walks on, right? And the x values are like the ground. So the domain is the ground you walk on. Alright? So the domain of a graph consists of all the input values the graph uses on the x-axis. The range. Alright, so how do I remember range? Well, range I think of when you go to the shooting range, which is when you're shooting things into the air, right? You're shooting things into the air, which should be upwards. So the range is a set of possible output values, which remember are the values that are the y values. So they're on the y-axis. So the domain, things on the ground, the range, things in the air. So note, given a function f of x, we denote the domain of f as dome f. Okay, so if you're ever talking about the domain, you write dome f, or sometimes dome f. And the range of f is written as range f. Alright, so let's first identify the domain and range of our graph. Well, the domain of our graph is, remember, going to be the x values. So the x values consist of 0 through 8. So the domain of our function, which we're not actually given an f, we're not actually given a variable for the domain. So we're just going to say the domain, and we're going to list out the numbers. So remember, we aren't writing domain f because we weren't given a function, we were just given a table. So the domain is the x values we have. That's the domain. So take a second and try to write down what the range values are going to be. Well, the range values are going to be all the values we used for the y's. Or you could also look back up at the table at the top. So the range is going to be, and we can list it out in smallest to largest. So let's go 126, 127, 130, 131, 133, 136, and 140, and there were a few duplicates. But there we go, that's the range. Those are the values we used for the y values. And remember the domain as the x values. Alright, so almost last and final question. During which weeks did Lynn's weight increase? We could look back at our chart, or we could look at our graph here. Where did our dot go from going downwards to popping back up? Well, the week that it popped back up was right here. The graph went from being down to up. That was from the 6th to the 7th week. She gained again. Because notice all these dots here were going downwards, and that plateaued right there, but then all of a sudden it popped back up. So she gained weight. So she gained weight between week 6 and 7. So she gained during, or you could say between week 6 and 7. And lastly, F, average rate of change. So the average rate of change is the change in your y values over your change in your x values. So this little symbol here means it's a delta, which means change. So delta, which means change. Actually, I'll leave that up there. Delta, change. So we want to find the change in the y values over the change in the x values. You're trying to figure out how things changed. Well, to do that, we're going to take the difference between the first and the last y values and the first and the last x values. So writing those down, let's see, our first x and y are 0, 140. And our second, or our last x and y is 8 and 126. So let's go ahead and label these appropriately. We have the x1 and y1 value. So when you label this, please remember, think of them as a married pair. Normally married people have the same last name. I know it's not always the case, but it's the normal thing you see. So these are the sub 1s. So we have x sub 1, y sub 1. And then these guys right here are the sub 2s. So plugging them in, y sub 2 was my 126, minus my y sub 1, which is 140, all over my x sub 2, which was 8, minus my x sub 1, which was 0. And what did I get? Well, 126 minus 140 is going to be 14, negative 14, all over 8. And we can go ahead and simplify these by dividing the top and the bottom by 2. And we get our simplified average rate of change, negative 7 over 4. So if I read this off, remember my y values, these guys right here, that was my weight. And my x values right here, that was the time in weeks. So what this is saying is that the weight goes down 7 pounds every 4 weeks. Not bad. Okay, so remember once again, I read that because the x values are my time and the y values were my weight. And that is it for Chapter 3, Cluster 1. Please email me if you have any questions.